So some basic definitions. So now please be careful with my notation. I know I don't draw very well. I meant this to be an uppercase F evaluated x. We will say that it is an antiderivative for a lowercase f of x over some interval I, provided that uppercase f of x has its derivative being equal to f of x for all values of x in that interval I. Now, I don't typically concentrate interval I, because I typically concentrate on just the domain of the function, but to be formal with my definition, I put it in. So given some function lowercase f, an antiderivative, say a function or an uppercase f of x, is simply a function as a quasi derivative equal to f of x. Now, when you differentiate a function before, when we differentiated, there was only one derivative. I'm going backwards now. With anti-differentiation, given a function little f down here, there might be a lot of uppercase f's. So take a peek at how, if f of x is equal to something like, I don't know, 2x, isn't this its antiderivative? Now, I do think I just said that out loud incorrectly. I said, isn't that, I guess I did say it correctly. I hope I didn't say, is this the antiderivative? Jeepers. I do think this is an antiderivative of this piece, because when you differentiate this, you get that. So I should have asked, I don't know if I did, can we come up with an antiderivative for f of x? And we can, and there is an antiderivative. But I think this is an antiderivative as well. Because when you differentiate this, you get the same thing. As a matter of fact, I could have tacked on any constant c. So let me state that in the form of a theorem, even though it's obvious. The general antiderivative for a lowercase f over some interval I is uppercase f of x plus an arbitrary constant, where uppercase f is simply an antiderivative for lowercase f, and you can put it over some interval I if you like. Oh, I should be underlining what I'm starting to talk about right here and what I was defining here. So I do think on your own you can probably recognize that an antiderivative for the cosine of x is the sine of x. An antiderivative sine of x is negative cosine of x, because when you differentiate that, that's what you get. An antiderivative for 1 over x is the natural log of x. As a matter of fact, notice this relationship. I shouldn't say equal, sorry, I meant arrow, my goodness. As a matter of fact, if x is negative, this is not defined. But since I started off with this, if I replace x with a negative number, it looks like it does not have an antiderivative, but it does. It's really just a natural log of the absolute value of x. And the book discusses this more clearly than I am. You just take the natural log of x or the natural log of the quantity negative x, differentiate, you get the same darn thing. And so when you tack on the constant c, you're really talking about the general antiderivatives for this 1, 2, 3 functions. So I will leave it to you to take a peek at the table 2 on page 352 of your text. Look at that table of antiderivatives. They're really easy to check, because you just go on the right-hand side, differentiate, see what you get on the left-hand side, if that's the order they're in. Now, I want to come up with displacement of a particle on a number line. So this is a simple little physics question. We typically think of position functions with the letter s. But the derivative of position is velocity, derivative of velocity, acceleration. In other words, given a function here, there's its derivative, here's the second derivative. But I'm starting off with the second derivative. And so if a of t is equal to what it is, then when I anti-differentiate to get velocity, I'll anti-differentiate term by term. In that table, you'll see what we call the power over anti-differentiation. See this power expression t to the n. You up the exponent by 1 to n plus 1, divide by the new exponent. Well, the new exponent is 2, So I get 6t squared over 2, or 3t squared. Anti-differentiating 4, I get 4t. You can double check me, see if I made a mistake. Differentiating this, that's what you get. Oh, by the way, get a constant, I'll call it c. Or maybe I'll call it c sub 1, since I'm probably going to anti-differentiate twice. Where, with this initial value condition right here, if I substitute in for t0 and simultaneously -6 in for v, then I see that -6 is equal to c sub 1. So if you allow me to rewrite this, I guess in particular my velocity is given by this algebraic expression in t. Oh shoot, I messed up. I didn't answer the question. So now to come up with the position function. Let's go ahead and anti-differentiate again. Using the power, is that going to give me this? But don't forget, we've got to tack on that constant of anti-differentiation. It's the second one, so I'll call it C2. Where I was given another initial value condition, namely that when t is equal to 0, the corresponding position, or s value, is 9. Does that give me that 9 is equal to a few zeros plus C2? So finally, my position at time t is given as such. There's my position function.